Every time we work on a project, we encounter data with certain domain-specific structures over and over again. Maybe you've built a simple registration form before and had to process an email from an email field. Perhaps you've also built a checkout and had to calculate the total price of a shopping cart, or had to save a phone number from an input mask. Let's look at a small example. For our website, we want to implement a simple user management system. So we have a data structure called user, which contains an email address and a phone number. For simplicity's sake, we'll leave out any additional fields for now. A possible implementation in PHP could look like this. We have defined two fields, email and phone of type string, where phone is optional and therefore nullable. We have also defined some getter and setter methods. When a new user registers, we want to send them a welcome email. For this, we'll build a small service that sends the welcome email. We have some kind of email client that sends the email, and we pass this as a dependency to our service. The send method is called after registration and receives the user object as a parameter. In the method itself, we do two things. We get the user's email from the user object and pass it to the email client along with the email content. But for a robust service, we should consider some error cases. Our email is a string, and while it can't be null, it could be empty. In this case, we want to throw an exception. Additionally, the email itself might not be a valid email address. In this case, we also want to throw an exception. With these two error cases handled, we have built a robust service that is easy to debug. What we've done here even has its own name: defensive programming. Defensive programming is a practice where code is written to anticipate and handle potential errors or unexpected conditions to ensure the system remains stable. In concrete terms, this means that we cannot rely on the parameters of a function always being within the expected value range. The larger and more complex a system is, the more important this practice becomes, as we cannot always know, for example, how another developer will use our functions in the future. But this approach alone has a major disadvantage. We have to catch the same errors over and over again. If we have many services that send emails, for example, then we have to catch the same errors over and over again. So what is the real problem? The thing is that we pass a parameter of type string to each function. It doesn't matter whether the parameter is part of our user object or not. We have designed our code so that an email is always a string. But what is a string anyway? A string is any string of characters, no matter how long, short, or complex. A string can be empty, but it can also contain thousands of characters. A string can also contain only one space or be completely empty. But an email is not just a string. An email is a non-empty string in a specific format. So an email is not just a string, but actually its own data type. But how could we implement such a data type? Just like we define all other types, we write a class that defines the desired properties of an email. In the constructor of the class, we expect a string, because we always want to create our new email type based on a string. This string is also stored in this class. In the code, we can then work with this type as usual. But so far, we have not changed anything about the functionality. Nobody is stopping us from creating an email that is not an email or is simply empty. That's why we simply add the validation directly to the constructor. We have thus created a mechanism that prevents us from creating an email that is not an email or is simply empty. Creating an empty email object is therefore no longer possible and leads to an exception. So that we can output our email again, we implement the double underscore to string method. This simply returns the stored string. We have now created a class that not only stores a string, but also defines the properties of an email. The existence of this class is only possible if the email is valid. An alternative implementation would be to move the instantiation of an email to a static method. This method would then return an instance of email if the email is valid, just like in the constructor. The difference is that here we have control over which data type we return. If you are not a fan of exceptions or your programming language does not support exceptions, You can use this method and return an error type in the event of an error, for example. To continue to prevent us from simply creating an email that may not be valid without the static method, we have to make the constructor private. Let's go back to our welcome mail service. Our service still has a dependency on an email client. In the send method, we no longer pass an entire user object, but our new email object. This eliminates all of our validation logic, as this email object is already validated by its mere existence. The method therefore only consists of a single call to the email client. Since our email object implements to string, we can pass it directly to the email client and cast it to a string. Of course, we could also continue to pass a user object here if we want to access further user data, for example. To do this, we can modify the user class so that an email object is stored in the user class instead of a string. We can now use our email directly via the getEmail method without further validation. We have created a so-called value object with our email class. Value objects are objects that consist only of values and represent an addition to existing data types such as strings, integers, etc. A value object can be identified by its values and not by an ID. Two different value objects are therefore the same if they have the same values. In many programming languages, the comparison operator can be overloaded for this purpose. Alternatively, we can also implement an equals method. This distinguishes value objects from other objects that are identified by an identity. This is automatically the case in programming languages such as PHP with a nominal type system. TypeScript, on the other hand, is a structural type system where objects can already be identified and compared by their structure. Another characteristic of value objects is that they are immutable. This means that we cannot change any values within a value object. To do this, we simply dispense with setter methods, for example, and encapsulate the values within the object in private fields. You have probably already come across value objects without realizing it. Many programming languages use value objects for dates, for example. In PHP, there is the datetime immutable class. This class represents a value object for dates, which is immutable. Value objects are a very useful and important concept in software development. But of course, there are also disadvantages. Even if I am of the opinion that 99% of software projects do not run into this overhead, value objects do add a certain amount of memory and computational overhead. Value objects also bring an additional level of abstraction and can make simple applications more complex. So when you are starting to use value objects in your projects? I'm looking forward to your comments. Thanks for watching and see you next time.